Hi, Year 13. We are going to continue looking at our conditional probability formula, but applying it to tree diagrams in particular today. So we have previously seen this formula here. Hopefully, when we were doing yesterday, looking at the Venn diagram stuff, we're all happy with how it works. The probability of an event A, given the fact that we know that B has already occurred, is equal to the probability of A intersection B divided by the probability of B. And we can kind of see that quite nicely from the Venn diagram. So if this is A and this is B, if we know that B has definitely happened, we're actually restricting the options from which we're choosing from. And we saw yesterday that we can either deal with that with actual numbers, frequencies in there, or we were doing somewhere we had probabilities on. So you might have a 0.2 there, 0.4, 0.3, and 0.1 outside. We can use this formula with the probability of A intersection B. We can just take the 0.2 divided by the probability of B, which would be both of those two combined. So we can see how it works from the Venn diagram. This formula, however, it is given to you on the formula sheet, just looking now. So you have got a section with statistics. You've got both the probability of A union B being equal to PA plus PB minus the probability of the intersection. So you're given that one, and then you're also given this one just beneath it. So you don't need to worry about remembering any of these formulae. So as I said at the top, we have already looked at this at GCSE in year 12 as well, but we're going to be combining them with conditional probabilities. So just going straight in, two questions in particular that I'm going to show you, and then the rest of this time you're going to be having a try of some yourself. You could have had this question easily at GCSE. It's not even a particularly complicated tree diagram, is it? We have got a bag with red and blue marbles. A marble is chosen at random but not replaced in the bag. A second marble is then chosen at random. Given, and of course it's that word there that is telling us that we're going to be using that conditional probability formula. Given that the second marble is blue, what is the probability that the first marble is also blue? It doesn't say draw a tree diagram. Some questions will. However, looking at this, you appreciate the structure. I think it certainly lends itself to easily being solved by a tree diagram. So I've got red and I've got blue there. I've got the probability of a red is 4/10, and the probability of a blue is 6/10. Now we know we can cancel those down. They're 2/5 and 3/5. But because we are then taking out another marble, I think if you keep it in its non-simplified form, because then we can easily say, okay, right, I've taken out one red. So if you go along the top here, I've taken out one red, take out a second red. Well, I can easily look at this fraction here, say, right, I did have 4, so I've now got 3. I did have 10, I've now got 9. If you simplify your fractions, I know you'll all be kind of wanting to because you're all excellent mathematicians, but if you simplify your fractions, then it means that you can't easily spot the patterns in the probabilities themselves. I know that underneath, okay, well, I picked out red, so all 6 blues are there, and then it's 6/9, and under here R and B. Okay, if I've taken out one blue already, I've got all 4 reds, but that is out of 9, and I've taken out one blue already. There's now 5 left, so that is 5 out of 9. And what you're doing at GCSE, you write down the probabilities at the end, don't you? You write down, okay, so 4/10 multiplied by 3/9 and so on. You work out all those probabilities, but let's be a bit more discriminate this time. Let's just work out what we need. That is our tree diagram. What we actually need to work out, given that the second marble is blue, what is the probability that the first marble is also blue? Right. Shall I first of all put R1, B1, R2, B2, R2, B2? Sorry, sounds a bit like a Star Wars robot. That, of course, is saying, right, red on the first pick and a red on the second pick, etc. So the probability that we need to work out, we need the probability of the first marble is blue. So I want the probability of the first marble being blue. So I've called that blue 1, given the fact that the second marble is blue. Okay, so slightly odd maybe, or there's a potential confusion, isn't there, because the given statement is actually written first, but that's fairly common. So you always need to write this statement here as the probability of the first thing given the second thing. Okay. I'm just wondering whether that was a confusing way to say it. So the fact that's given needs to be put second. Okay, that works. And then just use the formula. So I know that the formula is, so it's the intersection of them both divided by the probability of the second thing. So I want the probability of B1 intersection B2. So I'm just writing down the formula. I'll worry about what those things mean later over the probability B2. So on the top, we need the probability of a blue on the first pick and a blue on the second pick. So we need the probability of 2 blues. And then underneath, the probability of blue 2. So that is a probability of a blue on the second pick. And of course, that's something that I can easily work out from the tree diagram. I'm just going to rewrite this. And let's do it in a different colour as well. So that's the probability of getting 2 blues. So if I deal with the numerator first, the probability of getting 2 blues, that is just this particular branch here, isn't it? So the probability of getting 2 blues, the probability of B1 intersection with B2 is equal to 6/10 multiplied by 5/9. That is 30 over 90. And then if I work out the probability of the denominator, the probability of B2. So there are 2 possible options here, aren't there? So I can either go up this branch here, have a red on the first pick and then a blue on the second pick, or this one here. So of course I've already included that in the bit on the numerator, but the denominator, we want to work out the probability of getting the blue on the second pick, and this is how I work it out. It is the probability of getting the top branch is a red 1 intersection with a blue 2, or the probability of a blue 1 intersection with a blue 2. So that top set of branches is 4/10 multiplied by 6/9. The bottom set of branches, well, I have already worked it out, but I'll just write down 6/10 times by 5/9. Here again, you can see why it's tempting to cancel fractions, but if I cancel fractions, what I'll do is I'll spoil that lovely common denominator that I've got there. So I've got all these fractions that have got the same denominator of 90. I've got my two answers. So that means I should be able to go back to my probability. So therefore the probability of blue 1 given blue 2, so the probability of getting a blue, the first marble being blue, given that the second marble was blue, it's equal to that 30 over 90 divided by the 54 over 90. And again, because I have kept those fractions with the same denominator, they're of course going to cancel, aren't they? So if I just show you, 30 over 90 divided by a fraction is the same as multiplying by the reciprocal. So 30 over 54. Which is what I can divide both those by 6. 5 ninths. Okay. There we go. All right, so moving onwards then. This second one. I think the more wordy ones can sometimes be a little bit trickier. Yeah, we know where we are with the taking things out of buckets or whatever. The probabilities on each of those branches is really quite predictable. Looks a bit messy. Let's just get rid of those. So with this one here, we just got to be, I think, a little bit more careful about where we put our branches, where we put our probabilities. So we've got somebody traveling to school by car, by bike, on foot. 3 probabilities. The probability of being late when using these methods is 1/5, 2/5, and 1/10. Now, these are two kind of different kinds of probabilities. If you add together these three here, I've got 3/6, 1/6, and 2/6. They add to give 1. Okay, and that is because Fred presumably only ever travels to school by car, bike, or on foot. So it's one of those options. So all of those have to add together to give 1. But note here, these probabilities, the 1/5, the 2/5, and the 1/10. So if I change all of those to tenths, I'll have 2/10, 4/10, that's 6/10, 1/10, 7/10. They don't add to give 1 because, of course, they're not part of the same kind of event. They're not part of the same sample space, are they? So the probability of him being late and the probability of him being on time will be add to 1. We don't have that option here. We're not interested in that option there. So don't worry that if the probabilities don't always add to 1, they don't need to add. They don't need to add to 1. The first thing we need to do then, when we draw our tree diagram, I have got my 3 different transport options here. So I've got car, bike, or on foot, and the probabilities are 1/2, 1/6, and 1/3. So now we have the late and the not late option on each of these. So I shall put late and late dash for not late. And this is where you can see the probabilities are going to add to 1. So I've got the 5th there, and that is paired with a 4/5 there. Those two add to 1. I then have a late and a not late option there, 2/5 and 3/5. And then finally, I've got a late and a not late option at the end. Oops. Sorry, I should try and write a bit bigger, I think. So late here is 1/10 and late here is 9/10. Now, what I'm not going to do, I'm not going to worry about finding common denominators here, because I've got different denominators already here. I've got different denominators there. So I'm not going to, we're just going to have to deal and find common denominators at the end, or I guess use the calculator. Okay, so what we need, given that Fred is late, so we need to find the probability that Fred did not travel on foot, given that he is late. Remember, we have to put it that way around. So did not travel on foot, that is F dash, given that he is late. Okay, as soon as you write down that given statement, write down what the formula is. Don't worry about the tree diagram. Don't worry about what the symbols mean. Right, I've translated it into the symbol, so I'm now going to apply the formula, the probability F dash intersection L divided by the probability of L. Okay, so now we can look and see what those two different options refer to. The one on the top, okay, so he didn't travel by foot. That means he's either got to be by car or bike. But then he's also late, so it's going to be that branch and that branch, isn't it? So we want travels by car and he's late, and travels by bike and he's late. So that top one is going to be the probability of car intersection late plus the probability of car, not car, bike intersection late. The bottom, that is just the probability that he's late. We don't mind whatever means of transport it is there. So the probability that he's late, it's going to be that one, and also that one. So we're going to be going down those three branches. So on the bottom, that one there, probability car and late plus probability bike and late plus probability travels on foot and is late. So the numerator one, probability F dash and late is equal to, so I need to see the tree. So the first option, that one with that one, it is 1/2 multiplied by 1/5 plus bike and late. So I'm now looking at that option there. That is 1/6 multiplied by 2/5. 1/10 plus 2/30, that's 3/30 plus 2/30, 5/30, which is 1/6. So now we want to work out the probability of the purple ones. Probability of him being late is equal to, so it's actually the two options that I've just previously worked out. So that is the one at the top and that one there. The final one that I need is the one at the bottom, so the probability that he's on foot and was late, that option there. So I just need to add on the additional 1/3 multiplied by 1/10. I already know that these first two fractions simplify to 1/6 because that's what I got up here. And then I need to add on 1/30. That is 5/30 plus 1/30. 6/30. 6/30. That cancels, doesn't it? That is 1/5. So now I can go back to my overall formula, my conditional formula. Therefore, the probability that he was not travelling by foot, given that he was late, is equal to, so the green line, the probability that he was not on foot and was late, that is 1/6, divided by the probability that he was late. So that's the denominator. This one here, that's 1/5. 1/6 divided by 1/5 is equal to 1/6 times by 5/1. 5/6 is our answer. Okay, so let's get rid of this again. All those additional bits. So draw a tree diagram as you would have done at GCSE, and then just apply the formula. Just apply the formula, making sure that you write down these two things the correct way. Any stage your answer is bigger than 1, go back and check something has gone wrong. Okay, so that's all the new stuff to show you, and it really is just a matter of practicing what we've done, but practicing it with tree diagrams that you are probably more comfortable with than Venn diagrams. So in the rest of this lesson, there are only 3 questions. Okay, so please, please, please do these questions. The first 2 are fairly straightforward. This one, and I'm just looking, is that the same question? It is the same question. That's a little bit annoying. 4 and 6. So I am going to change this and put you a different first question. Obviously, I copied the wrong one in. So you'll have one simple one, just with 2 and 2 sets of branches. This one's slightly trickier because you've got a set of 3 branches and then another set of 3, another set of 3, another set of 3. This one is a slightly different situation, so you just got to be a little bit careful when you read this. But full worked solutions are underneath. So full work solutions. So please try the questions yourselves. If you can't do, then do check those solutions. Also, please contact me, Teams, and I should be able to get back to you at some point today. I'll also be posting a homework, so please make sure you complete that by the set deadline. Okay, thank you very much. Goodbye. See you next week.